The starting point usually for somebody who wants to do a design using HFWorks would be to build the model. And the purpose of this demo is not to show you how you build models in SolidWorks. Suffice it to say that SolidWorks is the #1 CAD package for 3D. It's quite powerful, so we'll not cover them. The purpose of this demo is really not to go in detail into any specific problem, just to give you an overview of how the software works and to see if it answers some of your needs and so on. We will try to show you that this is a very productive, very easy to use, highly productive tool for high frequency design. So I'll go ahead and pull up a piece, an assembly. So I'm picking an assembly, obviously the complexity, the level of complexity of assemblies that you can deal with is really limited by your ability to draw and build models inside SolidWorks. Okay. All right, so this is my assembly for somebody who has SolidWorks. They will get the standard tabs, the feature manager, the property manager, the configuration manager, and the display manager. When you add HFWorks, it's going to add this fourth tab. This is the HFWorks manager, and it's going to add this drop-down menu, which is the HFWorks menu. It will also add the HFWorks buttons here. Okay, so that comes with it. All of this is managed easily through the add-ins manager inside SolidWorks. So you can go. These are all the add-ins you can have in SolidWorks, and a couple of add-ins that are ours, HFWorks and Mini Atlas, are two add-ins to SolidWorks that allow you to do high-frequency electromagnetic design. Now, suppose this is the assembly we want to work with. Typically, for electromagnetics, the part of interest is the air, because this is what's going to happen. The wave is going to travel in the air. The metallic part that we see is what we need to build. And it has all the details down to the lettering and whatever. So in other software, this might be a problem. Working with such complex structure, you have to simplify, or you have to export it from SolidWorks to some other tool, and then work with the geometry, eliminate what you don't need and whatever. We do not do any of that here. Here, what we do is basically we work with the real part. This allows you to work with a part that's going to be manufactured, so you'll be exchanging information with your own design departments, your drafts people or whatever, so you don't have to have different bits and pieces, one for simulation and analysis and optimization, and one for fabrication and so on. Okay. So suppose this is my assembly. When I switch over to the HFWorks tab, I see the name of this assembly. And this is where you start working on the electromagnetic side of things. So what do we do when we want to get the simulation going? You go to your assembly and you right-click, and you have right on the top the study. So the concept that we use to define the analysis is what we call the study. So I'm going to study this part, okay, this assembly. All right. And I'm going to keep this as a study name, my first study. And right beneath that, I have an option of doing choosing the type of solver that the simulator is going to use. These are matrix solver techniques. The direct solver tends to use more memory, but tends to be slightly more precise. Tends to use more time as well in solving. The iterative solver is more, it's less memory hungry. Okay, so it's less memory. And it's also the solver that's parallelized, so you can use it as a, you can use the multi-processor that you have on your computer, of the multi-core processors. It will take full advantage of all the hardware that's available. Okay. So I'm going to keep default false for the time being. The skip 3D solution allows you to look at the model and basically, instead of solving the full 3D and waiting for the time that takes, you can simply just look at the ports where you're exciting your structure and you figure out if your structure is well dimensioned before you go ahead and invest in getting the full solution. Okay. So this is again the first step, which is defining the study, and gave it a name, which is the solver. Okay. And we have three types of analysis that we can do. The package comes, HFWorks comes with three types of analysis. One is straight S parameters, so this is for all kinds of microwave circuits, RF microwave circuits, multi-port single or multi-port circuits. And obviously, it will give you the scattering parameters of any given structure. Okay. If you're looking for the eigenfrequencies, the resonance frequencies of the structure, then you would choose an analysis type that's resonant. So in the S parameter, you're going to give it a range of frequency that you want to analyze over. In the resonance, you're looking for problematic or desired resonance frequencies. You want to make a resonator, you want it to resonate with a given frequency. If you're looking for spurious resonances, you do that to also find out where the circuit is resonating when it's not supposed to. So that's the second type of analysis. The third type is antennas. So if you're doing an antenna problem, okay, then you would choose antennas, okay, as the analysis option. And that in that case, there will be, we'll be looking at antenna parameters which we not find in microwave circuits. Basically, everything to do with spatial properties of antennas, the radiation pattern, the gain, the efficiency, all of those things can be computed for antennas when you pick the antenna analysis type. Now, as you saw, depending on analysis type, then I have to enter certain information. Okay. So now, if I'm doing this as parameters, I can decide how I'm going to switch, how I'm going to do the solving. So, if I want to sweep frequency over a certain frequency band, I can tell the solver do what we call a discrete sweep, which means solve at every frequency. Okay, then it goes through and does a full matrix solution. Or what we have what is called the fast frequency sweep. That uses basically what is known as model order reduction. And in doing so, we solve at one or two probable frequencies, and then extrapolate and get the response over a wider, much wider frequency band, a lot more frequency points. Okay. So that is the type of frequency sweep. You can define your range by start stop. So this is my start frequency. I could say 1 to 10 gigahertz, and I want, I don't know, maybe I want 21 points in there. Okay, and as soon as I click, it generates this my list of frequency. I can edit this frequencies and so on. So this is basically where you decide what your frequency sweep is going to be like. If I were doing a connector or a transition and I wanted to look at time domain data, we can check TDR. Okay, compute TDR is an option one you get with S parameter solving. So if you're interested in that, then you define the parameters for the rise time, the number of steps, and the number of time points, and so on. And this allows you to get the time domain response. Typically, a lot of connected people and transition designers, they would use that feature to look at the time domain impedance, the impedance of the function of time, which gives them an idea about discontinuity within the model. Okay. So basically, this is the first step. This is where we design, where we define the study type. So when you click a check mark, it says, okay, you're okay with this. Then the software goes and basically what it will do, it will create the structure of a study. So the structure of a study has three basic components that we need to work with. Basically the bodies, which are the solids. We need to tell them what materials are these made of. We need to also establish what we call boundary conditions, or loads and restraints. And we need to measure more. So these are the three steps you would do in getting a study going. So this is my first study. You can notice I have solids, where I have to define the materials. So if I look at this, I have all these solids that are inside model. So this is basically my part of interest, which is the air. And all of these other parts are part of the assembly. Okay? So that's the first steps would be to define the materials. The second step would be boundary condition, and the third step would be meshing. You do not necessarily have to do them in any given order. You can start with meshing, and do boundary condition, or do a little bit here, a little bit there, it doesn't matter. But before you can run a study, you need to set these 3 steps. Okay? So how do we do materials? Okay? Well, the materials, if you have a homogeneous material, you can apply material to all. Okay? Or you can select a few of these materials, these bodies, and you can go apply to select it. Okay? Or you can basically go individually and say, okay, this part, okay, I'm going to apply, let's see, this part is air, so I'm going to right click on this, and this is predefined air. And you notice that there is now a check mark. This part is defined. Okay. Now this part, actually, these other parts. Now, if I look at this part here, okay, I'm going to just zoom out a little bit. Okay. And I look at this part, for example. This is metallic. So I can say I want to apply this a perfect electric conductor. Okay. So that's a perfect electric conductor. If I want to know the rest of it, this part also is a perfect electric conductor. I can just go ahead and drag and drop. So that gets the same material property. In fact, if I go here and go into SolidWorks and do isolate, okay. So this is actually the part that's of interest to me. All the other parts are basically metallic parts. So what I can do this the other way. So I can say, and apply to, I can apply to all materials. I can apply PEC. And then I go back to my air part and I say apply air. And this is very quickly, I told the software what I wanted to do. Now notice one thing, that I did not have to do any simplification to do this model, to analyze this model. All I said is I want all of these parts to stay in, and I'm telling the software that these are conductors, so it will just ignore it when it does the simulation. So you don't have to play with CAD or play with the geometry and simplify things and so on. I also get the bonus in doing things this way, and the bonus is the following. Okay. When we go to analyze this problem, we're going to mesh the air. We are only interested in the air. Okay. So again, I go to isolate. Okay. So this is my air part. All of these surfaces are touching metallic parts. They're touching the metallic part. So all these surfaces need to have a boundary condition associated with them. Now the software knows when you have metallic part touching the dielectric or non-metallic part, it will apply a metallic boundary condition to that surface. So this will simplify considerably my analysis by doing things this way. Okay. All right. So let's say this is the material definition part that's done. When all of the materials are done, you see the check mark, so this is done. So the next step is boundary conditions. Now, if we look at this structure, this is a 2-port structure. So this is 1 port, and this is the 2nd port. So I need to basically tell it that I have 2 ports. So the way to do that is when you right click. By the way, these menus, they get configured according to the study type. So from doing antennas, I get slightly different boundary conditions than when I'm doing gas parameters or resonance and so on. So I want the port boundary condition, okay, and I need to select the surface. So this, if I select this, it adds it to my selection list, and this is port number 1. Okay, and I can tell it how many modes I want to analyze on. So this is basically the software can do what we call generalized S matrix. So we can do the S matrix from one mode to another mode. In other words, it can do what we call mode conversion. It can compute. If there is a mode conversion, you enter with one mode, and you exit at the same port or at another port in another mode. Okay? And the way to do that is basically to do, more modes. If you want more modes or less modes at the port. So let's say we're just interested in one mode. So we can do it like that. Now, if you want to compute also, you need to compute the impedance at the port. The software by default will compute what we call the power current impedance. Okay, it computes basically the power and computes the current and uses the definition of power, basically half Z, the impedance I squared. And from that, it will figure out the Z at the port. That will be the port impedance. If you want to compute it using the voltage definition, then it allows you to define a voltage path where you want to compute the voltage. So we can define a path to say, use the power voltage definition of power, okay, and compute the port impedance that way. Another feature in the ports is what is called the calibration, because when you do numerical solution, you might get the mode that this is a waveguide, so you can get the fundamental mode, TE10 can be pointing up or can be pointing down. It's numerical, so it's within a sign, it's going to find. So we can force it to orient your field the way you want. And then again, it's a calibration path. It will take the orientation of the path. It will go from this point up to this point. It's going to take that orientation and orient the field in that direction. So let's say, for the sake of simplicity, I define the port. Okay, it shows me that I have a port. I can go ahead if I have multiple surfaces and it's not here. I can say show, and it shows me with symbols where the port is. So that's my port 1. Okay. If I go ahead now and define my second port, it will increment automatically. So if I select this, okay, and say that's port 2, it added port 2 for me. And then I can see that that's port 2 or that's port 1. So these are basically, for this structure, this is what we wanted to do. We wanted to define 2 ports. The rest of the boundary conditions, the PEC, they are inherited from the materials. So like I was saying earlier, okay, all these outer surfaces, okay, they automatically get a boundary condition. All right. So basically, these are the two first steps. And I just wanted to maybe go back and open parenthesis. The software that we're showing you, HFWorks, is gold certified by SolidWorks. What does that mean? It means basically we adhere to all SolidWorks standards. So the menuing system, when you right-click and you say, okay, I want to see the properties, this is my study, we're using the same interface, same convention as SolidWorks. So if you're doing CAD or you're doing analysis, you don't feel it's a different environment. It's seamlessly and fully integrated. We go through a rigorous process of evaluating the software from SolidWorks before we get the gold certification. Okay. So SolidWorks has many, many partners, but few are what is called gold certified. All right. The last step we need to do before doing the study is to create the mesh. I'm not going to do the step of creating a mesh because I don't want it to take time in meshing, but I just want to show you that this is basically a fully automated process. So you can control the mesh size, the global mesh size. You can control the tolerance, which basically tells it if 2 points are less than a tolerance away from each other to merge them together. And we give you also a way to kind of have a control over the mesh, the number of elements per diagonal. So that will allow you basically to control the density in different parts in a complex assembly. So in this case, I say I want basically 40 elements per diagonal of an element. So when we click skip metallic parts, it will automatically skip all the methods. So it will not mesh it. So it will just find the parts that are dielectric and mesh those. Okay. And we have different options for controlling the accuracy of the mesh, basically to capture the curvature. So if you have a curved surface and you want to make sure that you get enough elements to capture the curvature, will give you full control there. Another feature in the mesh is what we call mesh control. So let's say, because this structure is quite big, and you wanted to control the meshing in certain areas. So you can say, for example, if I want to select this port and I want just to apply mesh control to this face, or you can apply mesh control to a whole body. Okay, so this is bodies and this is faces. So if I want this mesh to be different from the global size, I can make it bigger or I can make it smaller, or I can enter a value that I want. And if I say check, then I have a one mesh control. So I can have as many mesh controls as I want. So basically the mesher is fully controllable by the user. It's automated. You can do the meshing this way, and or you can do what we call the adaptive meshing. So the software can start with a default mesh and then compute the error and adapt mesh adaptively. So adaptive meshing gives you assurance that the results have converged, but it will take longer because every time it has to mesh and refine the mesh until it arrives at convergence. Once you become knowledgeable with the software, you will know ahead of time which areas are critical, and you can mesh them fine from the beginning, and then you can get to results much, much faster. All right, so basically, if we say that we've done this meshing, we have the materials, the boundary conditions, we've done the meshing, our study would be ready, and the way to run it is just right-click on it and say run. And then when you say run, it's just going to go and solve the problem and generate the data. So before we go to that second part, I just want to illustrate maybe one more feature. So let's say, for example, I've done this study, okay, and I want basically not to change much, and just to say instead of air, I want to fill this with some dielectric. So here is how we would do that in a very fast way. So you take this part, okay, this study, you drag and drop it on the assembly, and it's basically going to make a copy. I'm going to do a copy of my first study. Basically what I did is I basically duplicated or cloned that first study. So I have everything that I have. I'm going to click on my part here. This is here. And I'm going to now say apply material to this part. And now I'm going to show you how we do this through material library. So in the material library, we have a built-in material library, and that comes ships with the software. But you can create your own material library. So you can say new material library and create your own. Okay. So in this case, let's say I want to change this dielectric from air. Maybe I'm going to pick a cable dielectric, maybe a cellular FTP, and let's say check. And it's basically telling me a permittivity of 1.5, maybe it's 1.78, I don't know. I can switch it, check. Okay. All right, so basically at this stage, okay, I created a copy of the study. The only thing I needed to change was this. This study, without doing any further work, is ready to be analyzed. So I can right-click and run it. Okay. I can repeat this process as many times as I want. I can create multiple studies, so I can just copy and this is second copy. Okay. Again, and I can change the parameters that I want for this study. And once I have so many studies set up, we have also a feature called Run All Studies. So what Run All Studies does, it basically allows you to sequentially execute all the runs. So if you wanted to look at multiple material scenarios or something like that, then you can run all studies, set them up, and then maybe you might run them overnight or whatever. Okay, and then basically come the next day and find all the results ready. All right, so I think this is basically the first part of my demo, which is basically to show you how the software, basically how you can get the study set up. Okay, and at this point, I'm going to probably switch over to show you something slightly different. If there are questions, you feel free to type them into the message box. I'll try to answer them as we go along. Thomas, opening something slightly different now. All right. So what I'm showing here is basically it's a cavity filter, multi-cavity filter with what we refer to as tuning screws. Okay, so this is one of many applications. Obviously, the software is general purpose. It's based on the finite element technique, so it's not limited to any given structure or any given set of materials. Whatever you can draw, whatever you can model, and you know what materials are used, you can simulate and analyze and get data for. So the filter is just one example. Then the idea here is basically to show you one of the other features that we can use. So if you wanted to play with tuning this filter and find out the impact of different screw positions, well, we can use the configuration manager in SolidWorks. So we have multiple configurations. So I can say without screws, for example, I make this show this configuration. Okay. So you can see I can switch it over to this configuration. So I have no screws, or I can pick something else. I can show this configuration. And I can have a different set of configurations. Okay. So in this way, okay, I can within a single design have multiple iterations, if you will. Okay. And in HFWorks, the way we take advantage of this is basically we can define studies associated with configurations. So if I want to study this configuration, this kind of configuration, I can define the study for that. I can say that when screws are 1.5 millimeter, the first one, the second one is 1.2, etc., and so on and so forth. What is the frequency response? Okay. All right. So you can see here that for this structure we've done many studies, different studies, and we set them up. Each study is associated with one configuration, and we ran them all with this run all studies command. So we got a bunch of results. Now for this configuration file, okay, that I have, you will notice the three elements that I showed before. Basically the solid, the boundary conditions, and the mesh. So maybe here I can say, okay, I can show the mesh, 3D plot of the mesh, okay, and I can look at the mesh, okay, with coded, color coded. So the smallest elements are in red, okay, and the largest elements are in blue. So you can see that I did here, because this is, I expect high field variation near these screws, I have a finer mesh there, and the mesh becomes coarser as I go away from these elements. Okay, so this is a mesh. Okay, I can just, probably just also show the mesh in non-color plot. So this is, okay, but you can go ahead and also show the mesh in this way. You can also section clip. You can look at your mesh inside the model. So, okay, for example, if I wanted to look at the mesh in this section, I can say, okay, so I want to look at the section plot of the mesh, and then you can zoom in on that and see how is the mesh inside the model. So you can see that this is basically a section of the mesh. I'm looking at it at different angles. Okay. So in addition to, I showed you we have mesh controls here, so that's why we end up with a mesh that's finer near the screws, okay, and coarser as we go away from the screws. So that's a typical mesh that the mesher did for us. Now these are basically the study configuration part. These other folders are basically new folders that didn't show before, and these are created after the software has run and simulated the model. The first part is what we call the results table. So this is where we give you tabular data. So data in tabular format about your structure. So you can see here, this is your frequency list, and for each frequency you can look at different parameters. The S matrix, the normalized S matrix, the impedance matrix, the admittance matrix, the port characteristics, VSWR at the port, and so on. As you change frequency, these numbers change. Okay, so you can go and look at what is your data. And what you might do with this data is up to you, but you can export this, and you can export it in a text format or in Excel or standard formats like touchstone format or city file format for circuit simulators to use. So that's the kind of thing you can do. You can look at the numbers precisely this way and so on and so forth. Okay. So the results table is where we capture basically all the results that software computed, okay, for the structure. You have two folders where you do field results. So we have the electric field results. Okay. By default, the software is going to create at least one plot for us. Okay. But you can go ahead and create as many plots as you want. So I want to do a 3D fringe field plot at maybe some, I have, this is center frequency, I do this. And I can go ahead and basically from this plot, I can convert to a section flip plot. I can choose the plane that I want. Okay. So if I flip the plane in that direction, or the plane in that direction, or I can have two sections, one in one direction, one on the other. So I can have this kind of, the post processor is very powerful in this regard. So you can generate the plots that you want, okay, and once you say, okay, you're set, you can go also and do 3D vector plots. So you can generate that as well. Okay. So you can look at the data. Again, if you go to the vector plot and make this either into a section flipping of this, you can also go ahead and animate. Okay, so if you animate this, you see how the propagation is happening, okay, in your structure. You can animate any of the results. So it could be either animate the vector plot, or if I wanted to go back to my section plot, I can animate that as well and look at the data as it's propagating. So you can see I animate multiple sections simultaneously. So this allows you really very powerful, full control to look at what your model and what your design is doing. Okay. Again, so that was the electric field. You can do the same thing for the magnetic field or whatever. Okay. So these are the fields. You can also do 2D plots. So if you wanted to look really at field data between along the line in the structure, you can do what we call a 2D plot. So you need basically to do a 2D plot. You can say, okay, I want to look at the field between this point here and maybe another point on the opposite side, okay, of the structure. Okay. And when you say okay, it's going to go and generate, okay, well, they give me invalid points to consider. So I have to pick points that are really inside the model. Okay, so maybe I don't know if you can do this. So I have to here with this selection. Between this point and hopefully this point. Hopefully we can take these 2 points. And then if I just click here and auto scale this, and that's my field. And then I can probe this field, okay, point by point through that section. That's what my field is doing. I expect that it's basically the TE mode, TE10 mode. So I can look at that data. So I can look at the field in different modes. I can do these kinds of plots. I can do section, etc. I can go and do isosurfaces if I wanted to. So I can just isosurface only. So I can play with the surface value and what are surfaces of equal value. I can do 2 of them, so up to 6 of them if you wanted to. So these are 2 different surfaces. Isosurfaces keep adding. So if I do that, again, you can go and if you wanted to look at this, you can animate it in isosurface to see how these surfaces are propagating through the model. So this is the field data. Now, if I wanted to look at S parameters, this is an S parameter study, and I wanted basically to do S parameters, I can do either split shot S parameter or 2D S parameter. So I have a 2D plot here. Okay. Again, I set my default. I turned off my auto scaling, so I'm going to turn it back on. And then basically what I done here, I just looked at 4 curves, and I looked at 4 configurations. I put S21. This is my insertion loss or transmission coefficient. Configuration 2, 3, 4, and 5. And let's see the impact of the screws, because each configuration, 2 is this one, so it has a certain set of parameters for the screw position. 3, 4, and 5 are 4 different. Okay, I can create more plots the way I want. So I want a 2D plot of this study, and I just want S11. Okay. Okay. And this is my S11 for this filter. Okay. So I can go ahead and do as many of these as I wanted to. I can print these obviously, and so on and so forth. Okay. All right. So that basically gives you an overview of the way we do the study, basically setting it up, meshing, getting the solution, looking at solution results. The next step is to basically document. So documenting is very important, and we try to make that equally easy for users. So we have this folder called reports, and this is where we do the documentation. So the way we do it is we want to define a report. A report, when you click on it, gives you this dialog box. Basically, you can choose what the report is going to include. So it can include the cover page, an introduction, a description, file information. So you can, any of these elements you don't want. Let's say I don't have TBI, I don't want TBI. I don't have an appendix, I'm not putting that in. If I go to introduction, I can just, type in, this is my introduction. Whatever text you want. Okay, and so on and so forth. Okay, the background of your report, you can choose it to put it on any background color. Okay. And once you select what you want in there, then you choose the format. So you can put it in HTML or Word. Let's put it in Word for the time being, and we click OK. So once we click OK, the software automatically captures all information that's pertinent that you requested to be in the report. So you wanted the introduction, some file information, the field plots, and so on. So it went and created a Word document, okay, and it put it in Word. So if you were to edit your report file, you might expect to go into Word and open your document elsewhere and so on. But we don't do it that way. What we do is basically bring Word inside SolidWorks, inside HFWorks. Okay. So this is Word. Okay. This is the Word interface, and this is your report file. Remember, you said this is my introduction, whatever, more and so on. Now I'm in Word, so I have full Word capability, but I'm always in SolidWorks at the same time. I don't have to switch windows or anything like that. If I wanted to go to my results table or my electric field result, well, you recognize this plot that we made together. We made this section plot figure and all of this. Now I want to add text to this or change the title of it. Okay, this is not a good title. So you can just go ahead and change the stuff there. Okay, you want it to be maybe in a different color, whatever. So you have the full capability of Word inside of SolidWorks. So you can document your work as so. You can create different report formats. You can have something short, something long, something more detailed, something less detailed. If you wanted to put it, let's say, put it again let's say we put it in HTML. By the way, you can decide where to put it, so it's placed in a certain directory and so on, give it a file name and so on. So let's say I put, by default, I keep it in HTML, just to show that even if you put it in HTML, it's the same concept. It's going to stay inside. So you have the HTML. This is your HTML report. It's hyperlinked, directly hyperlinked. So you can just go electric parameters. This is my plot, okay, and back. And if I wanted to go to my field plot, okay, this is magnetic field. We didn't look at it before, but here is my electric field plot. Okay. And so you're navigating an HTML file. You can print, to do print preview, etc. So this is, if you want to publish this, put it on a web or whatever, you just copy the file, it's navigation ready and so on. So we can have multiple reports to document your work and your study. Again, the purpose is really to give you a feel of how the software runs, the features that it offers, and so on. Okay. We're not going into specific details, what's the performance of one device or whatever, or we didn't look at an antenna and see how we do radiation pattern or whatever. So it's just an overview of capabilities. The last point I want to cover before maybe closing and maybe opening for questions or whatever is this let's see, where is my task pane. Okay, so in the task pane of SolidWorks, we added this tool called Mini Atlas. So this tool is basically a transmission line calculator. Oftentimes for electrical engineers, we need to draw stuff dimension based on electric properties. Let's say I wanted to make a printed circuit line, so I would probably want a 50 ohm. Okay, a 50 ohm line that's 90 degrees long, quarter wave length at 2.545 gigahertz. Those are the defaults. And this is using this substrate, 2.33, and then dielectrics, that would probably correspond to a Rogers Deroyd 5870. Okay. I can change that substrate to something else, and they say, okay, I want always this 50 ohm, it's going to update the dimensions for me. So let's say this is the part I want. Okay, so we have this tool which hooks inside SolidWorks, so this is my part, and I want just to either insert it to an existing assembly, or I can create a new assembly from scratch. So if I click create, okay, now it's creating the part for me. So you will notice I create SolidWorks quit on me. Sorry about that. So while SolidWorks is restarting, I'm going to show you the full atlas, what we call the full atlas. The full atlas has over 70 transmission line structures. And you can do, for these structures, you can do analysis, you can play with geometry and find what the electrical properties are. You can do synthesis, go the other way around. You can do even what we call a 2D analysis. Let's say I have this coaxial line, okay, and I want to basically look at the field. So I can just do a quick simulation, come here, look at my mesh. So it did the 2D analysis, and then I can just go ahead and flip through and look at the electric field, okay, the result of the electric field, and I'll hide the mesh and see electric field in vector plot. So this is my vector plot of the electric field. I can do it as contour plots and so on. I can show the coax geometry on top of that. So I can play with this. I can look at the results listing. So this is basically a 100 ohm cable, okay, and I get that information from the finite element 2D software. So if this were an offset, you know, if I have some offsets here, offset the center conductor by, I don't know, maybe 6 mils or something like that. Okay. And I can simulate that and, you know, look at the slightly off center, okay, and I can look at the results of that as well. Anyway, so back to SolidWorks and to this. So if I say create now, hopefully this will work now. Okay. So I actually create an assembly, okay, based on the geometry that I defined here, without doing one single mouse click or one single drawing in SolidWorks. So I'm in SolidWorks. This is my coaxial line. It's an assembly. It was created for me directly here. Okay. Now, if you wanted to interconnect this to a coaxial line, for example, okay, again, I might want to put a I want a 50 ohm line, okay, and compute what dimensions that is. Okay. And I just insert this. Okay. So I have two parts. Now I can use SolidWorks, okay, to basically select faces. Let's see. I can select different faces. And then I just go ahead and make them together. So now it aligns those two planes together. Then I can move this one over here to make it coincident and make connections and so on. So very, very quickly, okay, we can make complex assemblies using this tool. Okay, you know, another example probably what people probably do sometimes is to make a coax to rectangular waveguide transition. So I can go to the waveguide, okay, and have this is a WR 2300 waveguide. Okay, so this is standard. If I wanted a different standard, I can pick a different standard. It's going to give my dimensions automatically for me. Okay, and then once I'm satisfied, I can insert this part, okay, and add it to my assembly. So I can be assembling very quickly, okay, complex geometries using, okay, this tool that gives us mechanism to dimension parts based on their electrical properties. Okay, so this is in this case, WR90 waveguide. So it's a standard waveguide. We know what the cutoff frequency for the first mode, some properties like the losses and so on and so forth, and then I could just insert it into my assembly. So this is a tool that is that's not yet released, but it's going to be released at the upcoming IMS. So for users to be able to basically accelerate even further the time, the modeling time, the CAD modeling time. Okay. So I think that brings us close to 3 o'clock. That basically, that's what I wanted to share with you guys today. I hope you I hope you guys enjoyed this. If you have questions, I'll hand it over to Adam. And if you have questions, you can type them in or.
Yeah, they can type the question in the chat box. If not,
so is Mini-Atlas is Mini-Atlas built in? Well, Mini-Atlas is basically a companion tool. It's not fully integrated with Solid.
You're welcome, Robert.
So I was answering the question. Question is Mini-Atlas built into HFWorks? It's not built in into HFWorks. It's an add-in to SolidWorks. It can be purchased separately, but it really is a companion to HFWorks. It's there to make the initial phase of CAD much more intelligent and much faster. And so the dimensioning questions and issues are resolved inside SolidWorks. We expect that it will always be bundled with HFWorks. But Adam will probably answer any questions about how it is bundled and the pricing and so on. That's something he's working on. And I know.
Yeah, sure. For any commercial questions, feel free, gentlemen, to send your questions to me at adam@emworks.com, right there. Okay. For any technical questions, please send your technical questions to Amar at emworks.com. So we all thank you, gentlemen, for attending this webinar. We enjoyed it, and this webinar is recorded, so it will be posted on our website starting from Monday, Friday, latest Monday, and you can always go back and be able to see it, from our website at www.emworks.com, emworks.com. In the webinar section, you'll be able to see it there and see it again. Thank you all, and you all have a great, afternoon. Bye-bye now.